So we were doing the kinematics, okay, the fluid flow, and I think we're going to finish today with the kinematics, yes, and start the conservation laws and the property dynamics the next time. Okay, so what we looked at the last time, we looked at tensors, okay, so we'll use tensors all the time. So we looked at the difference between writing things down in tensor notation and in vector notations. Then we looked at two theorems that we're going to use a lot. This is the Divergence Theorem, relating a volume integral to an area integral. Okay, so the divergence of your vector field volume integrated is equal to the area integral of that vector field, or the flux of your vector field through the surface. Okay, so that's useful if you have a control volume. You want to know what is happening within the volume. You have the divergence of your vector field within the volume, and that is equal to the surface integral of the vector field, which is equal to the flux of your vector field across the surface. Okay, so this is the Divergence Theorem that you can use a lot. And the Stokes theorem that we'll use today, it relates instead an area integral of the curl of your velocity of your vector field to the line integral of your vector field. Okay. So, okay, yes, we did that, right? Okay, so the curl of your vector field across a surface area is equal to the line integral along the line that is bounding your area. Okay. So that is useful because, okay, and then we define kinematically how to look at particles Lagrangially and in Euler form, and we define the Lagrangian derivative or the material derivative. Okay, so the total derivative of your vector field is equal to the local rate of change plus the advective derivative. Okay, so if you're following a particle, you can describe the change in that particle by the Lagrangian derivative. Okay, so basically, when you use a Lagrangian derivative, you're basically implying that you're following the particle. Okay. So you follow the particle and as it moves, so you can describe the changes in time and the changes in space due to the advection of that particle. Okay, then we looked at the streamlines, why they're useful and how you can define streamlines. So we derived the streamlines, definitions of the streamlines, and definitions of a stream tube, which is just a collection of streamlines that are passing through a curve, a closed curve C, the red curve C with that. Okay, so if you are integrating a flow around a stream tube, then you can use a collection of streamlines to define that stream tube. Then we looked at the deformations or the strains that an element of fluid can be subject to. Okay, so there were two main strains. One is linear strains and the other one is shear strains. Okay. So we look at rates of those linear and shear strains. And so we did this simple one-dimensional example of an element of fluid which is linearly deformed by this strain, and we look at the rate of change subject to this linear strain rate, okay, which is simply equal to that equation number 10, okay, in a one-dimensional problem. So that's the linear strain rate. You can also deform the element by shear. Okay? So you have that element of fluid, which is now subject to a shear strain. And so you can define the shear strain rates by looking at, again, this simple example. And you end up with this strain rate tensor E, okay? Which is giving you the diagonal terms is giving you the linear strain rates, okay? Whereas the off-diagonal terms are giving you half the shear strain rates. Okay, so with one tensor you can define the linear and the shear strain rates in the strain rate tensor. Okay, remember that we also looked at the velocity gradient tensor, okay, which is more, let's say, more important than this one because this is the general one. And the velocity gradient tensor had the diagonal terms that were the linear strain rates. And the off-diagonal terms, we didn't look at those, and we're going to do it today. Okay, so the velocity gradient tensor, the diagonal terms are the linear strain rates, and the off-diagonal terms are what we're going to look at today. So linear strain rates with the velocity gradient tensor, and the shear strain rates through the strain rate tensor E. Okay. And then associated with the shear, you can also define vorticity. Okay. So we looked again at a simple example, and we define vorticity to be the right-hand side of 13. Okay. And expression about vorticity. So we define vorticity of a fluid subject to shear stresses. It might acquire vorticity or it might not acquire vorticity depending on the shear stresses that are acting on the element of fluid. But more importantly, associated with vorticity is the concept of circulation. Okay, so you can associate concept of circulation to vorticity. So if you remember the Stokes theory, okay, this area integral of the curl of the vector field was equal to a line integral of the vector field, right? Where this is a closed contour that is bounding the area over which you are integrating. Okay? And so we define this line integral to be the circulation of u, in this case is a velocity vector field, around the closed curve, the closed line C. Okay? So the circulation of u around C is defined as this capital gamma, which is equal to this. Okay? So the line integral of your velocity field around that closed contour, and I will make this simple example of a bell shape. Okay? This is my bounding line contour C, and this is my area A. This is my ds. Okay. And so the curl of u integrated over the area is equal to the line integral around C. Okay. So the line integral around C is called the circulation of u around C. Okay. So this is what we define as circulation of u around C. So now you can go back to the vorticity and say that this gamma, which is equal to the circulation of u around C, through Stokes is equal to this, right? Stokes theorem, which we know what this is because this is the definition of vorticity. Okay, this is my vorticity. Okay, so this means that the circulation of u around a closed curve C, and we can shrink that surface to this surface A. Okay, this is my surface A, and this is my bounding contour C. If this is my vector field, in this case U. Okay. What circulation means is that the line integral of U around C is equal to the area integral of the vorticity of my vector field. In other words, the vorticity integrated over the area is called my flux of vorticity. This is my flux of vorticity through an area A. So if you have an area A and you have a flux of vorticity passing through this area A, that is equal to the circulation of your vector field. Okay. This is very useful when you are looking at geophysical fluids, because you might be interested in the vorticity of the fluid, but you cannot measure the vorticity of the fluid. Okay, so if you have an area, you can integrate your vector field along this area, along the bounding contour of this area, and you know that the integral of U around C is equal to the flux of the vorticity across the surface. Okay? A flux means that you have a flow crossing in a normal direction your area. So if this is your area and you have a flux of vorticity, but for some reason you cannot measure the flux of vorticity, you can integrate the vector field along the bounding contour, and that is equal to the flux of the vorticity, okay? Or the other way around. So that's circulation, okay? So the circulation around a closed curve, which is this, circulation of U around the closed curve C is equal to the surface integral of the vorticity, or in other words, the flux of vorticity. Okay, so we define the streamline and the stream function. No, sorry, we define the streamline and the stream tubes. Well, we can also define something else, which is a collection of streamlines, which is the stream function. It has a lot of practical ways. Practical is very useful because if you want to depict the motion of the fluid, you want to depict it, for example, in a two-dimensional case. The stream function is giving you a lot of information on the fluid. So what we do is we define a function that we are going to call, well, we're not going to call it yet. So we want to define a function that satisfies conservation of mass. We're going to do all the conservation laws next time. We're going to start all the conservation laws next time, but we can anticipate a couple of things today in order to derive the stream function. Right? So first you want to define a function that satisfies conservation of mass for obvious reasons. So if you remember the volumetric strain rate, okay, we did the one-dimensional example for the linear strain rate, and then we generalized that to a volume. Okay, so per unit volume, what is the change, the Lagrangian derivative of this volume? That was equal to, okay, so this was the volumetric strain rate, right? Starting from the linear strain rate, you generalize to a volume, that was the volumetric strain rate. Now, if you're following, so we're going to try to follow, because we are using the Lagrangian derivative, so implicitly we are following a particle, so the total derivative of that particle. So we're going to follow that particle in time, and we want to then depict the movement of this particle. And we're going to say that the volume V of this particle is inversely proportional to its density. Okay? The denser, the smaller for the same amount of mass, the denser, the smaller the volume, the less dense, the larger the volume. Okay? And we're going to try to follow that particle in time. So we're going to change now volume with density, and you can show that this is equal to this, rho is density. Okay, it's very simple to show this, they're inversely proportional. Okay. As volume increases, density decreases. Okay. And this is what we're going to derive the next time. This is called the continuity. This is the continuity equation. Okay? And we're going to derive this next time, probably. Okay? So we start with the continuity equation because we want to define a function that satisfies conservation of mass. Okay? So conservation of mass is the same thing as saying the continuity equation. Now what we're going to do, we're going to do another approximation that again we're going to define later, which is that density does not vary greatly along the path of movement of this particle. Okay, so density doesn't change very much as the particle is moving, so that any changes in rho primes are going to be much smaller than rho naught, which is the constant value. Okay, so you have, this is saying that you have a rho naught value, right? Whatever value of density you might have, and you have some small fluctuations around this rho naught, and these are the rho primes. Okay, the deviations around the rho naught. And so we're going to make this approximation that rho prime is much smaller than rho naught, so that density doesn't change very much along the path. Okay. And this is called the Boussinesq approximation. Okay, so we're going to make the Boussinesq approximation on the continuity equation. And if we make the Boussinesq approximation on the continuity equation, it means that any derivatives in density, so any derivatives in densities are going to be much smaller than any of the derivatives in the velocity field. Okay, so d rho by dt, d rho by dx is very, very small because of this approximation. Okay, so we can reduce the continuity equation to under Boussinesq. Okay, so the continuity equation under the Boussinesq approximation reduces to this, because any derivatives in rho are very, very small. So now we take a plain two-dimensional flow, okay, to make things easier and to then build our stream function. So under the Boussinesq approximation, we have du by dx plus dv by dy are equal to 0. This is my continuity equation under the Boussinesq approximation. Okay, and this is valid if w is not a function of z, right? So I don't have any dw by dz, which is a good approximation away from boundaries. And this also means that the flow is divergent free. The divergence of u is equal to 0. And this is necessary to build your stream function. Okay? The flow has to be divergent free. So now we have this continuity equation. And now we can define this function that satisfy the conservation of mass or the continuity equation. Okay. And we're going to define a function psi, which is a function of x, y, and time, not z, of course, because it's a two-dimensional flow, such that we have u equal d psi dy and v equal minus d psi dx. Okay, this is the function that I'm defining, and if I define my function psi this way, this is automatically satisfied. Okay, you put your psi here, and this is satisfied, and the continuity equation is satisfied. So I have defined my function psi that way in order to satisfy the continuity equation, because I started off by saying that I want to define a function that satisfies the conservation of mass. Okay. So by doing so, we have defined a this is also called a vector potential. Okay, such that my velocity vector is equal to that. Okay. And this is true for the case that we have built, so that psi is 0, 0, psi for a vector field u, which is u, v, and 0 in the z. Okay, so that's the function that I've defined that satisfies my conservation of mass, which is for a two-dimensional flow is simply this continuity equation. Okay, I define my vector potential psi like this. This satisfies the continuity equation. Okay, and in this two-dimensional problem, this is the definition of my vector field, the curl psi, so that I have a psi which is 0, 0 psi for the u that is only two-dimensional u and v. Okay. So you can define the vorticity of this.
Professor?
Yes.
Just one question. So the curl is a curl of a scalar quantity. Normally we take the curl of a vector. So that should be the third component of a sort of vector, which is 0, 0, psi z,
yeah.
psi 3.
Yeah.
Oh yes, it's written.
Sorry?
No, that was he said, and I didn't see.
Is this, right? Is it?
Yes.
See, his head is. So you can define the vorticity. What is it?
I thought I would shift and give him room to see.
No, he's fine. I'm sure he's fine. It was a joke.
Sure.
You're not convinced?
Tom was like, I'm also gonna.
What is it?
She said if I shift, I'm gonna be opaque to her.
Yeah, so you're always going to be in the middle. No matter where you go. That's very kind of her. So the vorticity is just the differences in the psi, okay? And we're going to see that that is going to be the reason why we define the stream function. Okay? So satisfy conservation of mass. This is my continuity equation. I make the Boussinesq approximation, so the continuity equation simply reduces to this, which is in a two-dimensional flow is just this. So I've defined my psi, which is going to be my stream function. With this, the sign is just a convention. You can switch the signs, it doesn't matter. But this is the convention that is usually used. So now this is your psi. So why is that useful? You can go back to the streamlines. And the equation for the streamlines was dxu equal uyv. Okay. And so now we can write this in terms of our new function psi. Okay. So vdx is going to be equal to u dy. Or simply this is equal to 0. Okay? So this means that along a streamline, psi is equal to 0. Okay? So the stream function is defining your streamline. So along a streamline, psi is equal to 0. So a streamline, equivalently, you can say that a streamline is equal to, well, how can I say it? Streamline is psi equal constant. Okay, so if you have the streamlines, you can build your stream functions, of course. So the equation for the streamline is also giving you the stream function. So along a streamline, the stream function doesn't change. So along the streamline, psi is a constant. So a simple example of why this is useful, not just looking at the streamlines, but looking at the stream function. Because if you look at the streamline, you know where the flow is going, okay? But you cannot compute fluxes. Okay? You cannot compute fluxes. It could be mass flux or volume flux. You want a stream function to do that. So let's have an example of these two streamlines or lines of constant stream function. Okay. So this is psi 1 and this is psi 2. And this is my point x and this is my x plus dx. Okay, so this is my segment dx where I want to compute my flux, for example. So now I go here and I have two components of the flow here. I have my v dx and I have my minus u dy. Right? So the total flux through this boundary has two components, u and v, which is v dx and minus u dy. Okay, so I want to compute the flux there. So the flow across this interval dx is going to be minus u dy, but u is dip psi dy minus plus v, which is minus psi dx. Dx. Yes. Okay. And this is simply minus the difference in psi. Yeah. So for this case, what it's telling you is that if you want to compute the flux through this segment that goes from psi 1 to psi 2, what is the flux passing through this boundary is simply psi 2 minus psi 1. Okay. So if you know the value on a stream function, on any stream function, then you can compute the flux through the boundary, which is simply the difference between the two stream functions. Okay, so if you have your velocity vector, you can build your streamline. If you have your streamline, you can build your stream function. And then you can plot all your stream functions. And for example, this stream function is a streamline of, so this is a constant, this is a line where the stream function is a constant, which is also a streamline. This could be equal to any value, okay, 20, whatever. This could be equal to 10. How can you measure the flux in between these two stream functions? It's just the difference between the value of these two stream functions. Okay. So if you just have the streamlines, you have pictures like this. Okay, but there's no information on the flux of volume or mass that is going along this flow. Okay, this is just depicting the velocity field, but you don't know how much flux is going in between those two streamlines. You want to build a stream function that is u psi dy and v minus psi dx. Okay, so you know your velocity vector, you know how much is u and v. You build a stream function and you get all these stream functions here. And for any place in x and y, you know the value of this stream function, psi 1, psi 2, psi n. Okay. So what is the volume flux or the mass flux going in your plot over there? Streamlines are not useful, but if you have a stream function and you have a numerical value for the stream function, the flux is simply the difference between the two stream functions. Okay. That's why they are so useful. And we use stream functions a lot. For example, in the atmosphere, you take the velocity vector in the atmospheric flow, wind, okay? You have a u and a v component. In space, this is latitude versus height, okay? You have a model or you have observations, you have u and v, and you build your stream function. Okay. So all those different colors are different values of stream functions. Every line there, there's no particular line, but okay, so this one, this is the equator. Okay. So these are closed stream functions, and this is stream function 1, and then we have more stream functions. Okay. And you build all your stream functions. Okay, so all these stream functions, they come from the velocity vector. Now you have those stream functions, and every stream function, which is a closed stream function, has a numerical value associated with it. Okay. So you know what is the flux in between the stream functions, and given the sign convention, you know which way the flow is circulating along the stream functions. Okay. So in this case, red means positive, and bluish means negative circulation. Okay, positive circulation is clockwise, and negative circulation is anti-clockwise. Okay, because of the sign convention. And so if you take your velocity vector in the atmosphere, you build a stream function. This could be a time mean stream function or just a time t. And you can clearly depict the atmospheric flow as a function of latitude and height. Okay, the example that we gave was upside, there was a function of x, y, and time. Here there is a stream function which is a function of y, z, and possibly time. Okay, so this is what we're looking at. Stream function, there is a function of latitude, height, and maybe time. Okay.
Professor,
Yeah.
might it be that the convention is opposite to the sign?
No, I think that's right.
Because if we start, for example, from the center of the yellow cell and we move to the right, but the gradient is negative with a minus sign, V is positive, so the flow should be up. The B component is positive.
So if this is my equator, and I have this stream function and this stream function, okay? So this stream function, let's say, is 10, and this stream function is 5. So numerically, I'm solving this as dip psi dx, right? So this would be 10 minus 5, and whatever x you might have, c minus 1. So that's positive, and it should give you negative. Then maybe the convention here is different. This is the opposite. Strange, because this is the usual convention. The V is man upside. I'll check how this was meant. Anyway, this is the
It's not important.
no, it's not important. As long as you know what convention you're using, it's not important. But it's strange, because this is the usual convention, and that's the usual convention, so it's puzzling. But so the important thing is that if you know the velocity vector, you can build a stream function with whichever convention you might want to use. And then you can depict the stream function of the atmosphere and get all these different structures. And all this, you will see this in atmospheric dynamics. This is called the Hadley cell. There's one on each hemisphere, and these are called the Ferrel cells. Okay, they are closed circulations. They're basically driven by heating at the surface. Okay, so at the equator you have a lot of warm sea surface temperature is warm and land is warm. The atmosphere gets warmed, gets less dense, and it tends to rise. So you see those two black arrows close to the equator. So the air tends to rise, and then it closes the circulation, and then it sinks at the mid latitudes. Okay. And so it closes that Hadley cell roughly around the equator. So with the stream function, you can clearly see the circulation of the Hadley cell and the circulation of the Hadley cell in the southern hemisphere in this case. And then you have another Ferrel cell which goes the other way around here. Okay? And you can build stream functions which are a function of time, and you can build the variability of your circulation. Okay? So you plot the stream function, or in this case, this is also called the meridional overturning circulation. It's meridional because it depends on the latitude, And it's overturning because thinking of warming and cooling is overturning the atmosphere upside down. Okay, so you have a meridional overturning circulation in the atmosphere, and you also have a meridional overturning circulation in the ocean. Okay, so you do exactly the same thing. You take a velocity vector u and v in the ocean, so oceanic currents, okay, in the latitude depth plane. You build your stream function, which is all those black lines. All those black lines are stream functions of a different value. And you can depict the overturning circulation in the ocean just as we did in the atmosphere. Okay? And so you see different cells, as in the atmosphere, you see different cells. So as the convention goes, this is, again, is positive, so it's clockwise. So you know that the circulation is going clockwise, sense around these positive values. And this is negative, so it goes anti-clockwise. Okay? And you can see this through the stream function.
Is that a zonal average over the Atlantic Ocean?
This is global.
Global.
This is global. So this is the global meridional overturning circulation, and it's actually integrated zonally and then integrated vertically to get the total mass flux or volume flux in the ocean. And so when you do that, you end up with a stream function psi, which is a function of latitude, depth, and the units is, after integrating, is meter cube seconds. Okay. So this is the velocity field in meter per seconds, integrated zonally and integrated vertically, so you get a meter cube per seconds. So this is how much mass, or you can multiply this by density, and this is how much volume you are transporting between the two streamlines. So each streamline has value. For example, this is 24, so this means 24 in Sverdrups. Okay, and one Sverdrup is actually 10 to the 6 meter cube per seconds. Okay, so this is 24 times 10 to the 6 meter cube per seconds circulating in the ocean. Okay, on a time yes.
When you look at the circulation in the atmosphere, they are almost symmetrical around equator. They are symmetrical. We hardly see in southern.
Because the atmosphere is easy.
Yeah. But on the ocean, I think the continents are the problems for the. Oh, okay.
Yeah, so we're going to talk about this in the ocean dynamics
Okay.
course. But basically, the short answer is that the atmosphere is easy and the ocean is more difficult. In the sense that, no, seriously, is that so the atmosphere? I have a couple of nice diagrams. So you can take the atmosphere, okay, and build your stream function on a two-dimensional flow. So I will try to use my skills. Okay, this is my Earth. This is the equator. Then you get this Hadley cell, Ferrel cell, and then the polar cell. Okay, so you build this. This is a stream function. Okay, this is my stream function that I constructed from the velocity field. And I've done that by, let's say, chopping the atmosphere in one location and making the flow two-dimensional. I can integrate zonally or just taking up somewhere over the Earth. Okay, so say here, this longitude, what is the meridional overturning circulation through a stream function, which is a function just of latitude and height, and you get this nice cells, the Hadley cells, the Ferrel cells, and the polar cells. Okay. If you cut the Earth here, or if you cut the Earth here, you're basically gonna get the same answer. Okay. Because if you're staying away from the continents, if you're staying away from the boundary layer and friction with land, it doesn't matter where you look at the atmosphere, you're always going to get 2 Hadley cells, 2 Ferrel cells, and 2 polar cells, okay? Because the flow is quasi-2-dimensional if you're staying away from topographic effects, okay? So many of the theories in the atmosphere, they're built on 2-dimensional flows. It doesn't really matter where you are, okay? Especially when studying eddies, mean flow, eddy interactions. You just study a 2-dimensional flow, it doesn't matter, okay? Now things are going to get harder. This is Americas. Don't laugh. And this is, obviously, this is Europe and this is Africa. Okay? So now, if you're trying to build this meridional overturning circulation and you want to make the flow 2-dimensional, if you're cutting here and then you integrate zonally, you're going to integrate zonally up to the zonal boundaries. So you're going to get one particular flow. If you cut in the middle of the Pacific, you're going to get a totally different solution, because once you integrate zonally, it's going to be different, totally different. And the circulation in the Atlantic and in the Pacific, because of the geographical boundaries, is different. Okay. There are many things that are common. So this is global. So this has been integrated globally, Atlantic plus Pacific plus the Indian Ocean. Okay, you integrate zonally everywhere, and you get this total meridional overturning circulation. But you could plot just the Atlantic meridional overturning circulation or just the Pacific meridional overturning circulation, and they would be different. In the atmosphere, if you cut in the Atlantic or if you cut in the Pacific, it's roughly the same. Okay. But there are things that are common. So these 2 cells, you see this is clockwise, and this one is anti-clockwise, and they're very trapped at the surface, roughly 400, 500 meters. Those are driven by the winds. And these are called subtropical cells. So these subtropical cells, you find them in the Pacific, you find them in the Atlantic, you find them in the Indian Ocean. Because as long as you have an equator and some winds blowing, you build these subtropical cells. And you can build your stream function of these subtropical cells, and you get very similar answer. If you integrate zonally in the Pacific, which is roughly 3 times as wide as the Atlantic, the value of the stream function is going to be much larger, because the total volume flux integrated zonally is going to be much larger in the Pacific than in the Atlantic. It's just a geometrical factor. But the structure of the cell is very similar. Whereas this cell, okay, this deep cell down to 1,000 or 2,000 meters, this is a meridional overturning cell that exists only in the Atlantic. You don't find, if you do the same stream function just for the Pacific, this cell doesn't show up. Okay, because this is only due to the Atlantic component. So if you integrate in the Pacific or if you integrate in the Atlantic, you get this, but you don't get this. So it's totally different. Okay, so that's why a stream function is useful. You have your streamlines, but streamlines are not telling you much about the flux. Okay, you want to know the flux. Perhaps you want to know the flux of vorticity of this flow, and you can relate the flux of vorticity through a surface as the line integral of the velocity along the bounding curve. Okay, so if you just have the streamlines, it's not very useful. So you build a stream function. You build a stream function. This is it. You build a stream function of the velocity field, and with the stream function, you know the structure of the flow, and you know the transport. Okay, you know the transport of volume or the transport of mass of your velocity field. Okay, so every time you see a plot like this of the ocean or a plot like this of the atmosphere, you know that's it's a stream function, and with a stream function, just with the numerical value of the stream function, you know the total flux in between 2 stream functions or streamlines.
Excuse me.
Yes.
To ask a simple question. Why are you saying that the flow across dx is only minus d phi? Why not minus 2 d phi?
Yeah.
Yeah. There are two components.
So I have VDX, which is mine.
That component plus the other component in x, because only it's changing phi.
No, what did I do? So I have VDX, which is minus, what is that one? Minus dip psi dx, then minus u dy, so minus dip psi dy. So the flow across dx has two components. It's vdx minus u dy, right? So v is positive and u is negative. Okay. So v is minus this one. And then I have minus u, which is positive. This is minus deep psi. So the flow across the dx is just the difference between the two stream functions bounding the dx. Okay, so we're gonna do this. So we define the streamlines and now the stream functions. We define the linear strain rates, and from the linear strain rates we define the velocity gradient tensor, and the diagonal terms were the strain rates, the linear strain rates. Then we looked at the shear strain rates, and we defined the strain rate tensor E. And then we looked at the vorticity, and related to the vorticity the circulation, and then the stream function. Okay, so now we're going to put everything together and say what is the sum of all the changes to my particle fluid, which is going to be the sum of all the deformation plus the sum of all the rotations. So the linear strain rates, the shear strain rates, and the possible rotation acting on the element of fluid. And so we're going to define the relative motion near a point. Okay, so the element can both deform and rotate. It can deform linearly, it can deform under shear, and it can rotate. This is my x2, my x1, and my x2. So now we're going to look at what happens to this element of fluid between point A and point B. Point A is at position x, and it has some velocity vector u, whereas point B has some velocity u plus the u at some position x plus dx. We have followed the particle from point A to point B. So now we want to define what is all the motion happening to the element of fluid, which is the sum of all the deformations and all the rotations that are happening to the fluid. Okay, so we do again Taylor series of our flow at u xi plus dxi at point B. Okay. And this is my ui xi plus everything that is happening at dx. Tensor notation is just this. Okay. So now I can say that my this is my relative velocity at time t. Okay, which is that component over there. But we know what this term is. What was this one? This is just the velocity gradient tensor. dy by dxj. And so the velocity gradient tensor will have all the deformations plus all the rotations that the particle of fluid has experienced as going from A to B. So if you remember, the velocity gradient tensor had the diagonal terms that were the linear shear rates, right? And the off-diagonal terms, we didn't talk about those, and this is where we're going to feel all those diagonal terms. So now we can decompose this velocity gradient tensor, which has all the different components, and we can define this velocity gradient tensor as this. Okay, so this is just half of the velocity gradient tensor plus half of the velocity gradient tensor, fine. And this is half of this minus half of the same, so I'm not adding anything, okay. I've just decomposed the velocity gradient tensor into two parts, and now these two parts are going to be very different. This is happen to be the symmetric part of the tensor, whereas this is the antisymmetric part of the tensor. And if you remember those two tensors that we talked about the last time, there were the velocity gradient tensor, and there was another tensor that was the strain rate tensor. Right? That was the strain rate tensor. So this is exactly that, the strain rate tensor. So in the velocity gradient tensor, we had the diagonal terms that were the linear strain rates, but there's also the strain rate tensor, this tensor E can also be included there. And the antisymmetric tensor is actually the rotation tensor, or actually half of the rotation tensor. So in the velocity gradient tensor, you have the strain rate tensors and you have the rotation tensor. So the velocity gradient tensor tells you everything about the deformations and the rotations, if you write it that way. Okay, so the strain rate tensor E if you look at all the components, you have E plus 1, E2 plus 2, and E3 x3. Okay, and these are the linear strain rates. Okay, these are the linear strain rates, which are my okay, so this is the diagonal terms. And the off-diagonal terms, you can look at all of them, but just going to write one. This is going to be half the shear strain rates. Okay, that's the strain rate tensor, where you have, which is just the symmetric part of the velocity gradient tensor, and in the strain rate tensor you have the linear strain rates in the diagonal and half the shear strain rates in the off-diagonal terms. Okay, so we knew this one. You can just look at all the components if you like. Whereas the rotation tensor are Ij, which is the antisymmetric part of the velocity gradient tensor, has diagonal terms that are equal to 0. Okay. 1, 1, minus 1, 1, 2, 2, minus 2, 2, and so on and so forth. And the off-diagonal terms I'm going to work this one as well. And so on and so forth. The off-diagonal terms are the components of the roticity. That's why it's the rotation tensor. You have 0, 0, 0. This is actually the third component, minus omega 3, and this is omega 3. This one is omega 2, and this is minus omega 2, and this one is minus omega 1, and this is omega 1. So the rotation tensor has diagonal terms that are equal to 0, and the off-diagonal terms are all the components of the roticity vector. So with the velocity gradient tensor, you have the linear and the shear strain rates given by this tensor. You have all the vorticity components given by the rotation tensor. You can show that this can be written with the alternating tensor like this. That's my vorticity. And so the rotation tensor, if you play a little bit with the tensor, is minus the alternating tensor and the vorticity vector. Okay. You can try this out. If you do R1, 2, this is going to be 1, 2, 1, 2 repeated indices, 0. 1, 2, 2, 2 repeated indices, 0. Minus 1, 2, 3, omega 3. This is 1 plus 1. So this is minus omega 3, which is this one. Okay, so you can write the rotation tensor in a much simpler form using the alternating tensor, and you don't have to expand all the components. You're just interested in what is usually your interest around the third axis. This is going to be the component you're interested in. Okay, so to summarize everything, you want to know what is the relative motion near a point, and what is the total sum of deformations and rotations on your fluid particle. Okay, we have this relative velocity. So dy is this velocity gradient tensor, which is that, plus half of the rotation tensor, dxj. Okay? So this is the relative velocity point B. I can express that with the strain rate tensor and half of the rotation tensor. So if you remember this, you can use it here. Dij dxj minus the alternating tensor omega k dxj. Okay. So you can also show that this is equal to minus ijk vorticity dxj. This takes a little bit. And so if you replace this here, dxj plus, now there's a minus here, plus I've dropped the minus 1/2, so now it's plus 1/2 of the vorticity dxj. So you can express the relative velocity at some point with all the deformations and all the rotations that this particle of fluid has experienced, with the strain rate tensor and the rotation tensor, which we have written now as the vorticity. So this is the relative vorticity velocity. Due to all the deformations, because in here there is the linear strain rates and the shear strain rates, and this is the relative vorticity velocity due to the rotation of my element of fluid, which is rotating at this angular velocity half of vorticity.
And in effect, if we substitute omega over 2 with angular velocity, we get just the motion of a rigid body.
I mean, you're assuming with the vorticity, you're just assuming that is the angular velocity of a rigid body. Okay, so the summary is that you can just take the velocity gradient tensor and play this game of separating the velocity gradient tensor into two parts, symmetric and antisymmetric part. The symmetric part is the strain rate tensor, and the antisymmetric part is half of the rotation mass. Okay? So that the velocity gradient tensor, we just talked about the diagonal terms that were the linear strain rates. Actually, the velocity gradient tensor has everything in it. The velocity gradient tensor is made of the strain rate tensor, so all the deformations, linear or shear, plus all the rotation associated to this relative velocity. Okay. So your relative velocity is going to be the strain rate tensor plus the rotation. Mistake?
When you substituted the rotation tensor, you repeated the dxj again. Sorry, the omega cos.
So I'm writing right. Yes, there's an angle. Thank you. Because this is the angular velocity at some dx distance from the axis of rotation. Yes. Okay, so if you're interested in the relative velocity of your element of fluid, you can just express that with one tensor, which is your velocity gradient tensor, which has all the deformations and all the rotation tensors. So this is some big tensors, and you put these two together, the strain rate tensor plus the vorticity of the fluid. But because we're using tensor notation, you don't have to expand all the components. Some of these components, or many of these components, might be zero. Vorticity might be zero. There might not be shear stresses or linear stresses to this acting on this element of fluid. So the total result is going to be just those components which are not equal to zero. So you might have vorticity or not, you might have linear stress acting on the element of fluid, and so on and so forth. And so this is, whenever you're studying, especially in solid earth, you're going to use a lot of shear stress tensors and linear stress tensors and rotation tensor acting on the element of fluid, and this is where all those tensors are coming from. What did I say?
When you talked about these being used in the solid earth, I was.
You say, okay, I'm not going to use that. You might use it as well. I mean, it's nothing special. Right? It's just three tensors, and you have to put them together. And well, if you're doing any kind of fluid mechanics or even geophysical fluid dynamics, you use many of these. Perhaps you use these after they've been massaged and chewed into a different tensor or a different conservation law, but this is where they're coming from. And so we're done with the kinematics. So this is how you describe your flow. You describe your flow with streamlines, you describe your flow with stream functions, you describe your flow through the vorticity, okay, but you still don't know why the fluid is moving. Okay, so we haven't talked about forces yet. We don't know why there are those Hadley cells or these meridional overturning circulations in the ocean. Okay, this is a way of showing the movement of your fluid particle, but we still don't know why. And so this is what we're going to start doing next time. We're going to start looking at the forces acting on the element of fluid and all the conservation laws acting on the element of fluid. Okay. Which is a little bit more fun, hopefully.
So when we look at that equation, we almost specialize that the rotation deformation is important in atmospheric and oceanic dynamics, and the deformation, the linear deformation is important inside the Earth, or for solid Earth.
No, they're both important in both fluids. I mean, vorticity is crucial in geophysical fluid dynamics, but
the assumption is
But I suppose that vorticity is important also in fluids in parts of the Earth.
Yeah.
That's right.
the outer core.
It must be. I mean, you have all the kind of instabilities, in radio Benard instabilities in solid Earth as well. It's actually probably more important there. So all those kind of instabilities where vorticity plays a role is also they're also present in solid Earth studies. So they're all
The
important.
assumption for the rotational deformation is that there is no volume change in the for rotational deformation. There is no volume change. Volume change is not important in the rotational motion, and that means linear.
So the only thing here that goes from angular velocity to vorticity is assuming that it is a stiff body, is rigid, rotating. So that's the only assumption that I made. Other than that, in the stream functions there were a couple of assumptions. So we made the assumption of the Boussinesq, so density doesn't vary very much, so the continuity reduces to 0 equal the divergence of the flow. And then we made the assumption of that's it, two-dimensional flow. I mean, you make a two-dimensional flow and you use the Boussinesq approximation.
I think